and welcome you to the fourth day's lectures. Today's first lecture and sixth in the series is on the moon by Dr. Neeraj Srivastava, Physical Research Laboratory, Ahmedabad. Moderator of today's first lecture is Ms. Neha Panwar, a PhD student at Physical Research Laboratory working under the guidance of Dr. Neeraj. Over to Ms. Neha.
Good evening, everyone. I'd like to take this opportunity to introduce the speaker for this session, Dr. Neeraj Srivastav. Dr. Srivastav is a planetary geologist serving at Physical Research Laboratory, Ahmedabad, as an associate professor and head of the planetary remote sensing section. He received his PhD from IIT Roorkee, India in 2015. Dr. Srivastav pioneered planetary remote sensing for geological studies in India at PRL in 2002 and contributed to the formulation of the scientific objectives of the Chandrayaan-1 mission ISRO. It was the first planetary endeavor from India. As a science team member, Dr. Srivastav has contributed to the analysis and interpretation of the data received from APXS payload on board the Pragyan rover of Chandrayaan-3 mission. In addition, he is deeply involved in the planning of the future planetary missions of ISRO, such as in the ISRO-JAXA LUPEX mission and the Lunar Sample Return mission. Dr. Srivastav has carried out research on various aspects of geology of the moon, and in particular, known for his discovery of recent volcanism on the moon. Earlier, the moon was unanimously considered to be a geologically dead body, but he, through his research, highlighted one of the prime regions where we do see active volcanism. He has also established a state-of-the-art laboratory for carrying out reflectance spectroscopy of planetary material and their analogs under simulated conditions. Dr. Srivastava is a recipient of the inaugural COSPAR Outstanding Paper Award for Young Scientists, Scientific Commission B in 2008, and the LPI Development Award USA in 2013. Over to you, sir.
Thanks, Neha. Thank you so much for your nice introduction. And a very good afternoon to all of you. And let me take this opportunity to thank Dr. R.P. Singh, Director IIRS, Dr. T.P. Das, Director SPO, and Dr. Praveen Kumar, Deputy Director SPO, for giving me this opportunity to talk to you all about moon. Let me first share my slides. Is my slide visible? Neha, is my slide visible?
Yes, sir.
So in this particular talk, I will be telling you how moon formed, how it evolved in space and time, how our understanding evolved in due course of time. This is very important for you, for the students who have joined this lecture, because that forms a basis for you to work out what should be done in future. So how this knowledge has evolved with time, this is what we will be seeing throughout this lecture. And then if I ask you regarding this, that when moon started, when was the exploration of moon started? Any one of you would answer me, it is something around the late 50s or the late 60s, early 70s that moon exploration started, but that's not exactly true. And you would be glad to know that moon's scientific study started in 1609 when Galileo Galilei pointed his telescope towards the moon. With these crude drawings, he could make out that the surface of the moon is rough and uneven, and just like the surface of the Earth itself. Prior to that, it was understood that moon surface is just a perfect sphere. There are no depressions, there are no mountains, and how he found. It's very important to understand, know this. You can see in this part there is a shadow, in this part there is a sunlit area. So this type of things, the shadow is a very important indicator in remote sensing analysis. Okay, so the telescopic observations continued for a long time. Hello? Yeah, it continued for a long time. However, as I told you just now, most of our understanding about moon came from the 6 Apollo missions, which from Apollo 11 to 17, which are shown here in the color, this green colors. Okay, you can see. So these green colored areas were those areas from where manned landings were carried out and samples were collected and brought out to the Earth. And then there were 3 Luna missions between 70 and 76 in this part of the moon, from where additional samples were brought robotically. So from these samples, we learned how not only moon, a planetary system should form. That type of, precious samples were these, and I will come to those in a few moments. Then there were orbiters. There was a gap of about 2 decades. Moon lots is important. People felt they have learned everything about moon, but that was not the case. And I will come to the details later on. But you can see here, there were 2 missions in 90s, and that is Clementine mission and Lunar Prospector mission. These were remote sensing missions. And these remote sensing missions gave a global perspective about the moon. What is the variation in mineralogy? What is the variation in topography? All those information came from these 2 missions. So in the next few slides, you will see what we have learned from the sample return missions and Clementine mission. So here, these are the 2 sides of the moon. I'm pretty sure that none of you have seen the far side of the moon from the Earth. And the obvious reason is tidal locking, astronomical phenomena. Okay. So if you see both the sides of the moon, the near side and the far side, they are quite different. And what do you see? Huge dark areas on the moon, which are present mostly in circular area, circular sort of mountains inside. If I say mountains, it is difficult to tell you here, but yes, these are the mountains, and these are the depressions where you have this dark basaltic plains. Okay, now this type of areas are dark because they are made up of this type of rocks, which have abundant FeMg rich minerals. I will not use any technical jargons, so you try to remember it is FeMg rich minerals, due to which these are dark areas. Then these type of areas are light because it is made up of calcium aluminum rich minerals. Okay, so that is why which is known as anorthosite, but you should remember it is calcium aluminum rich mineral. Then if you see here, it's a very nice feature with lot of rays here. Actually, this is a crater called Tycho crater on moon. Okay, and you can see the lot of rays. So why do we see rays on moon? Because this is also same composition. This is also same composition. However, their maturities means these areas are old. These areas are young. So any young area will be having higher albedo than the older area. So this is how moon surface gets its soil. Okay, due to the impact of solar wind and due to the impact of micrometeorites, it becomes dark with age. Okay, so one of the impact of the object which came out during the impact which produced Tycho crater was found very at large distance, and it has caused a landslide. Just imagine how much mixing would have happened. This is just around 85 kilometer diameter crater, and it has thrown material up to this distance. So these are very large ones. So these are basically called basins. I mean, any crater which is having diameter greater than 300 kilometers are called basins. Okay, and these are craters. The smaller ones are called craters. Fine. Now let us see this far side. Now, why it looks too different? It's a very big question in lunar science. There are certain hypotheses which explains. One hypothesis says that this is thick. This part of the moon, the crust is thicker, due to which the magma which came up from interior could not come out. That is why you don't see them here. But that is also debated, and it is still a big problem. Now, if you see here, there is a very low, there is quite a low albedo area here. What is this? This is South Pole Attican Basin on the moon. Okay, this is the largest impact basin on the moon, which is having a diameter of 2,500 kilometers and a depth of greater than 8 kilometers. This is one of the oldest basins on the moon, which is about 4.25 billion years old or more. The moon should have broken by this impact, but it did not. Why is it so? This is another question in lunar science. Let's see these craters at a in a zoomed in view. See, the craters range in size from micron size. This is a micron size crater, and as the size increases, this is a simple crater, simple bowl-shaped crater with a flat floor. Then you can see we see a central peak coming up. The crater walls are also terraced. So this is a complex crater. This transition on moon occurs at a diameter of about 15 kilometers. So you have to remember these things, and this varies. On Earth, it will be lesser than that because it is dependent on gravity of the planetary body. So as the size increases and we move on to the basin related things, it is 320 kilometer in diameter. You can see this peak, central peak has converted into a peak ring. And then at around 1,000 kilometers, you see multiple rings in this basin. So as a function of size, the morphology systematically changes. Okay. Now, this was this was the first study from our country where we have used this central peak data. We found the composition of the data, and for the first time, we told what is there in this subsurface, because these central peak, they tell us what is present in the subsurface, maximum depth. If you study a 100 kilometer crater, it is a 10 kilometer depth which you are sampling. And then we found that, number of plutons or mantle rocks we could find out on the moon. And the take-home message from this slide is that craters serve as windows to the interior of the moon. So from remote sensing, we can just study the surface. But if we know the morphology and we study the walls, the central peak, then we can tell what is there in the subsurface also. Well, coming on to the major volcanic features on the moon, then as I told you, there are vast basaltic plains. Then we have pyroclastic deposits, which is outcome of explosive activity on the moon. This is silent volcanism, this is explosive volcanism. And then you can see here the cobra head. These are the lava tubes. Okay, here from this part, this magma has come and the lava flew in this. This is the largest, you can say, sinus relay on the moon, and this is known as Valles Cotteri. Then there are few silicic domes on moon. Okay, when the viscosity is high, the viscosity of the magma is high, it cannot flow to larger distance, just accumulates like this and produces a dome-like structure. So these are the major volcanic features on the moon. Now, if we put age, because unless we talk about age, we cannot, really quantify things, how things have evolved. So this here, the cratering history of the moon is shown. So you can see during the early time, the moon was impact, the rate of impact was very high. Then it dipped around this 4.4 giga-annum, it dipped. Again, around 3.9 giga-annum, there was a peak. Now, this period is called lunar cataclysm or late heavy bombardment. Then after that, the intensity has fallen down and still it is like this. So this is how the impacts have happened on moon. Just imagine about Earth. Similar situation was there on Earth. So many impact happening and around 3.9 giga-annum. What would have been situation on the Earth? This is a very intriguing question. Then volcanic history of the moon. When those dark plains were formed on moon, a lot of them were formed during the early phase when moon was having a lot of internal energy. At that time, this 3.9 giga-annum, greater than 3.9 giga-annum, lot of volcanism happened. Then the main phase volcanism was between 3.8 to 3.1 giga-annum, and up to 1.2 giga-annum, it was the late phase. This was our understanding of the volcanic history of the moon when before our Chandrayaan and missions flew. Well, now see, Jolliffe et al. In 2011 used all sorts of data sets, compositional, morphological, remote sensing, sample, everything, and he classified moon into different type of crustal terrains, different type of areas, you can just say. Okay, for example, this area, just take it, this is known as Procellarum Greek terrain. Don't go into this technical term, just remember it is enriched in heat producing elements, radioactive elements, that's all. Okay, then if you see this area, the South Pole Attican terrain. So this type of terrains were felspathic highland terrain. So this type of terrains were formed by Jolliffe et al. Well, so here I have summarized the origin and evolution of moon theories on the basis of all those observations I just mentioned. So moon formed due to giant impact hypothesis. Okay, a Mars-sized object called Theia impacted the proto-Earth. Then what happened? A disk of debris was formed, and this disk coalesced to form moon. What happened afterwards? Afterwards, there was a lot of heat inside the system because of accretion. It is due to accretion, moon has formed, right? So there was a lot of heat. This heat has molten the moon, okay? And a lunar magma ocean was formed. So what happened in the lunar magma ocean? Crystals, when it started cooling, crystals start forming. And those crystals which were having light, means enriched in calcium and aluminum, they floated on the top, forming this crust. And those crystals which were having higher iron, magnesium rich minerals, they are seen in this part. So they settled in this part, forming the mantle of the moon. Okay, so giant impact hypothesis followed by global magma ocean hypothesis. These two explains, one explains how moon formed, the other explains how the crust of the moon formed, how the differentiation of moon happened, crust, mantle, core of the moon formed. Okay, then suppose your moon has formed around 4.4 giga-annum. What happened? Mare volcanism happened. Then formation of basins, as I told you. And I will just show you a movie which will give you a better feeling right now. Are you getting the voice? main phase of paravolcanism. Okay, so while they told us many things about moon, several new questions also arose, and some of them are listed here. Do we have water on the moon, or it is bone dry? Lunar prospector gave indication of presence of hydrogen-bearing compound, but whether it was H2O, they could not confirm. Samples were found to be bone dry. Then is the available samples in the repository sufficient to cater to the geological diversity of the moon? Means whatever sample we have from those missions, is it sufficient or we need new samples? Then what is the geological state of the moon? Is it geologically dead after 1 giga-annum? So these are some of the compelling questions which actually led to a new era of lunar exploration, which started this smart one, and you can see our Chandrayaan missions here. Okay, Chandrayaan 1 in 2008, 2 in 2019, 3 in 2023. So number of missions have gone to moon to answer these questions, and these are only few which I've listed. Okay, there were several questions. Before I go to some of the results, selected results from this, since they are students, they would be delighted to know that we now have a crater on the moon. This is a simple crater on the moon. This part, in this part of the moon, which is named after Dr. Vikram Ambalal Sarabhai, the father of Indian space program. Okay. And this is an incredible view of the moon from OHRC on board Chandrayaan 2. This is the best resolution data available from any mission. You can see boulders, small craters in the area, and these data have played a key role when we landed on the moon during Chandrayaan 3. Okay, now coming to the findings from Chandrayaan mission, you can see here for the first time on the basis of this particular depression in the reflectance data, okay, around 2.8 micron, it was found that moon surface is having hydration. There is a surface hydration of moon surface, and you can see in the polar areas, the hydration was found to be more. Hello? Okay, then these deposits, I'm in a meeting, please. So then you can see here, these deposits of ice mixed with regolith are present in the permanently shadowed regions of the moon. At poles, these regions have not seen sun for 2 giga-annum. Okay, so these areas have not seen sun, very cold, about 70 Kelvin is the temperature there. So any water molecule which has come to this area should stay there. Okay, thus it can be inferred that the moon is not bone dry. Now coming to the new rock types on the moon, as I told you, yes, there were lots of rocks which have not been sampled during Apollo and Luna missions. And one example is this Mg spinel anorthosite. This is a gemstone Mg spinel, MgAl2O4. And this is found normally at depth in Earth. But on moon, there are surface exposures of this. And this rock, this mineral, in combination with this particular rock, has never been reported from in more than 380 kgs of lunar samples. So this was a really surprise finding from the Chandrayaan-1 data, MQ data. Then there were potential exposures of mantle rocks around these big basins of the moon. And one example is shown here. So these are the mantle rocks. Earlier it was thought even these big basins cannot bring out the mantle rocks of the moon onto the surface, means the rocks from the very deep interior of the moon. But this thought process has changed now. Now people expect the mantle rocks on the surface. And here, these are the rocks on the moon which are yet to be sampled. Okay, only 2 examples I'm showing you. There are many more. Then coming to the recent volcanism of the moon, at this near side, far side boundary on the western limb of the moon lies the Oriental Basin, which is the prototype multi-ring basin on the moon. And this in the northwestern part of this basin lies a tiny crater which is known as Lowell crater. And Lowell crater is hosting one of the very exciting area on the moon. And this area actually, you can see here this type of things. If you go to Hawaii, you will see this type of dark flows and structures. Okay, but on moon, the first and foremost thing which comes to anybody's mind is that this crater forms, lot of melt will form here, impact melts, and this will just flow and make this area unit. But our detailed study showed that it is not as simple as this. These are actually volcanic eruptions on the moon, which would have happened merely 2 to 10 million years ago. And this indicated, you just see this zoomed in views using LROC NAC camera data, and you can see superposed flows, pit surrounded by vesicles, then pit showing extrusion of melt. I mean, so many evidences were there, even spectral evidences, composition-wise also we could actually see that this composition is different from the target rock, which actually proved our point. So the moon had volcanism around 2 to 10 million years ago, and thus the moon is geologically active. This is what we proposed. Now, here we further, you can see this is another incredible view of the flows in the same area. You can see these are superposed flows of different generation, and here faults and fractures have formed. So we have recent volcanism, we have recent tectonism. These flows are confined by a topographic barrier. So this source has to be here, okay, which is shown as Z, crater Z here. It's tiny crater, okay. We further, studied this area, the whole Lowell crater, and found that it is a very important crater on a moon, which can address to several important questions on the lunar geology, like its, nature of the mantle of the moon, mantle rocks could be present here, and several other which I already discussed. Now the question was, what is fueling this recent volcanism on the moon? And to answer this, we have to move in different areas. So what we did earlier, people, whatever 1.2 gigaannum volcanism I talked to you, they were found mostly in this area. So people have proposed those heat producing elements, which I mentioned earlier, were responsible for the volcanism on the recent volcanism on the moon. But what we did, we took this particular area. Here we found Lowell crater, and here there was already report. So we selected this area, and we were delighted to find nearly 700 million year volcanism in this Grimaldi Basin, and tectonism as early as 50 million years. The moon is geologically active indeed. But, well, if you move to this area actually we started a new type of study on moon. These basins are so old, they are so degraded, they're not seen. Only a little bit of depression in this area, but there are some basaltic areas which we can see here, small craters, small lakes of dark areas. Okay, so for the first time, we studied geology of an obscured ancient impact basin on the moon, and We also found recent volcanism in this area, up to the late phase volcanism, 1.5 giganum. Okay. So then we move to this Australian North, and this Australian North, this is a very unique basin here in this part, just in the western limb of the moon, eastern limb of the moon. This is the eastern limb of the moon, and here this basin, for the first time, it was reported by Grail. There is absolutely no evidence of this impact basin in the area. This is lost, completely lost. So Neha, actually, who is the moderator of this study, of this presentation, she carried out a detailed analysis based upon the understanding of impact basin and found late phase volcanism occurred in this basin also. And I will just tell you that this is the Scaliger crater and this is the Lacus solitudinus. She found this volcanism, recent volcanism in Lacus solitudinus. Okay, and this is a big pluton. Pluton is a technical term, a big subsurface magma body. Okay, that is Pluton. It could be the largest massive Pluton on the moon, okay, which is shown by Scaliger crater. Okay, and this basin could be even older than South Pole Attican basin. Just simple thing, don't get into the complexities here. This was the heat producing areas. And if this is only responsible for the young volcanism, then why we are getting in so many areas? This is a big question. This means something else is fueling volcanism on moon, recent volcanism on moon. That is what we have to understand in future. So we wrote a new volcanic history of the moon, the topical phase. This was what we added. And then we brought down the late phase to 700 million years. These are my concluding remarks. The missions to the moon during the past decade and a half have considerably changed our understanding. Geologically, the moon is much more diverse, and contrary to the expectations, the moon shows evidences of recent volcanism and tectonism, and it is enriched in volatiles. These findings are not in agreement with our earlier understanding of the origin and evolution of the moon. So our understanding is changing. To address them, new samples are required and in situ missions are required to address these issues and put forward another giant leap in the field of lunar and planetary exploration. So we have already selected few potential landing sites on the moon for in situ and sample return missions. There are several, but these are the few ones. And each of them are very important. Okay, if we see here, Renner Gamma, this will tell you about the magnetic anomalies of moon. Grimaldi Basin, recent volcanism, tectonism, as I told you. Then Compton-Belkovich, silicic volcanism, endogenous water. Endogenous means from the interior of the moon, not from the outer sources. Then South Pole Attican Basin, this is, I told you, okay. Okay, so, and you can, why you should miss this, Shiv Shakti point in the South Polar Highland region. If we study this, we can tell about what is the composition, what is the nature of the South Polar Highland region. Is it different from other areas? So multiple missions with varying capabilities are required to address these questions. And also you should think from now onwards, where do we want our Indian base station in the future? And that is why I just put this slide to show you everybody is moving towards the poles. Do we also need to move toward poles for Indian base station? Because pole has water ice. This is the known thing. In the equatorial belt also, we have lots of advantages. For example, we have natural habitats, lava tubes, abundant key natural resources are there. We have to think, you have to think, not me now, it is you, because you will be witnessing this thing in future. And the journey has just begun, long way to go.
जी हाँ, आप अपनी स्क्रीन पे देख सकते हैं कि हम लैंडर मॉड्यूल.
People are applauding. Let
लैंडर
us all
मॉड्यूल
wait to hear from the Secretary, Department of Space and Chairman ISRO, Shri S. Somnath.
लैंडर मॉड्यूल पूरी तरह से सेफली और सॉफ्टली चंद्रमा के सतह पे लैंड हो चुका है। ये हम लोगों के लिए बहुत ही गर्व की बात है। हिंदी में एक कहावत है कि चंदा मामा दूर के, लेकिन अब हम ये कह सकते हैं कि चंदा मामा अपने घर के।
बहुत ही उम्दा।
So if Chanda Mama is apne ghar ke, then it means Chanda Mama is for mankind. So I would like to end my presentation with a statement: let's explore the moon, not exploit it. Thank you so much.
Thank you, sir, for hello.
Yes, Neha. Over to you.
Yeah, so yeah, thank you, sir, for such a lucid presentation. And I hope the kids who are viewing this are actually excited to have a look at how moon has evolved over billions of years. We do have some questions from your talk. So a question by Balaji M is, sir, how much amount of water was in the moon?
See, right now, Balaji, what we see is some few hundred ppm of water in the this glasses. Okay, in the moon rocks, what we are getting is few hundred ppm, 300, 500 ppm. Okay, there was an experiment, LCROSS, right? LCROSS reported they have impacted in the KBS crater, a permanently shadowed crater on the moon, and they found that around 5 to 7% of water was there in this plume which formed due to the impact. Yes, Neha.
Another thing by Jadeja Shaktiraj. So what is late bombardment, and can it be used to explain it in the deep? Like, I think he wants to know more about the late heavy bombardment in detail.
Okay, so late heavy bombardment, as I told you earlier, is a time period around 3.9 giga-annum. Okay, so around this time period, all those big basins on moon, okay, say Oriental Basin, this particular Imbrium Basin, Serenitatis, all these big basins formed around this 3.8 giga-annum. Okay, so this is lunar cataclysm or late heavy bombardment. Now, the point which is to be noted here, why there is a question mark here. Okay, you can see the spike here. Apollo people did a wonderful job at that time. Okay, they collected samples from the moon surface. But the problem is, as I have shown you, Tycho ejecta has gone more than 1,000 kilometers. Okay, so it is a very big possibility that a very young basin in this area, the last one to form, maybe this is the Imbrium Basin, which is a very young basin in this area. And if I go and collect samples from this area, I may be actually collecting samples from this single basin. So I am actually getting only one event. If that is so, if there is sampling bias, then what will happen? All my ages will come here. Okay, so through different type of logics, people try to find out if a particular sample could be due to could have come from this particular event, that particular event, and that is how they have dated different basins, different impact events. But there is a very big possibility that this may not be true. So if that is so, then there may not be any peak. You just have a simple decline in the impact rate. So that is why it is put a question mark. And this also leads to future thing that when now we go to sample, we should be very careful. And now we have lots of information about some remote sensing missions, and we will definitely make sure that this type of question is minimized in case of moon. Yes, I hope I answered this question.
So there is this question by Akshat Sharma, which he asks, why is landing on the polar region of the moon more difficult than equator?
See, it is not like, landing on the moon in the polar regions is more difficult. I will tell you something about from my perception. Polar region, okay, is also highland region. Highland regions are normally uneven. Okay, so that is one reason why it is difficult. Second thing is that in this particular polar area, we don't have this flat areas. Flat areas are very less. For example, there is a Malapat mountain which is permanently lit. Now, this Malapat mountain, if you want to land, you have to be really very precise. Then only you can, go there. So polar areas there is another problem I will tell you. There is the sun angle. The sun angle is always very grazing, which can cause lots of optical effects. So if you want to, really land in an area, what you do, you have there is a lot of autonomy built in the system, and this autonomy can easily be, confused with what you see there when you go and land onto the moon because of very, very grazing sun angle in these polar areas. So that is why it is very challenging to land in the polar areas. Otherwise, it is quite rough. Available areas are very, very small, so pinpoint landing is required. Yes.
Muktorshi Das has a very interesting question. Is it possible that anytime a new moon will be born?
Yes. Is it possible that anytime new moon will be born?
That's the question he poses.
Is it possible that, yeah, I mean, see, theoretically, if you say, if you go by giant impact hypothesis, then what happened? Theia impacted this Earth and moon formed, right? So there is always a possibility in future you can get hit. But what will be our situation? I cannot comment on that. If if that type of small hit, okay, is responsible for the dinosaurs getting lost on the Earth, okay. So if that type of body hits, yes, technically moon can form. If a body like Theia still hits, it will be different scenario because it was proto-Earth at that time. Earth was also evolving. So it will be completely different dynamics. But yes, one new body can form. In fact, one of these hypotheses why there is a thicker crust on the far side, there is a hypothesis of two moons. So one moon has collided on the far side, and the material just coalesced onto the far side. Therefore, it is thicker than the thinner near side of the moon.
A question by Kolachalam Sai Charan is there. He asks, sir, as compared with the NASA moon landing, is really liftoff from the surface possible without any effect to the lander and ejector?
No, the question is not clear. Tell me what is the question? So
basically, I think he's asking that when we are trying to take a lift from the lunar surface, so the lander and the ejector that is there to, aid that liftoff from the surface of the moon, will they be influenced in any form?
Yes, they all will be influenced. When there is a liftoff, the nearby regions will also be influenced. Just as when we land, the nearby area gets influenced. When we take the liftoff, those areas will again be influenced. Yes, any more question?
Yeah, so I think these are the questions that we have today from the chat. So thank you, sir, for this talk, and I would like to hand it over to the next speaker. Thank you, everyone.
Thank you, Neha. Thank you so much. Thank you, everyone.
Thank you, Dr. Neeraj. interim in the Chandrayaan-2 project at NISR, Bhubaneswar. She did her integrated MSc Physics at NISR. She is developing an algorithm for the open source software to process the Chandrayaan-2 IIRS data. Such a software interface may enable the well-established open source ISIS software to process ISRO's planetary data sets. Over to Ms. Nivedita. Nivedita? Guneshwar Thangjam, as well as today's moderator, Nivedita. Over to Nivedita. I have already introduced Nivedita. Okay.
Thank you. Thank you, Dr. Praveen. Hi, good evening, everyone. It's my pleasure to introduce our speaker, Dr. Guneshwar Thangjam, and introduce him. Dr. Thangjam is a faculty in the School of Earth and Planetary Science at the National Institute of Science, Education and Research in Bhubaneswar. His academic and research journey spans various areas in planetary science. After completing his master's in geology, he worked as a junior research fellow at Space Application Center, where he worked at the analysis of lunar geology and morphology using the Chandrayaan-1 mission data. So he worked there from 2009 to 2012, and from 2012, he pursued his PhD from the prestigious Max Planck Institute for Solar System Science in Göttingen, Germany, where he studied the surface composition and geology of the asteroid Vesta using the NASA Dawn mission FC camera, FC instrument. So from there, he continued his postdoctoral work in MPS, where he extended his research of small bodies on the asteroid series using the Dawn FC and VIR instrumental data, hyperspectral data. And he also, as one of the team of the FC team at the MPS, he contributed to the Dawn mission operation by working on the FC data preparation and the calibration. So at 2019, he joined the NISA, and currently his research group is working extensively on the surface compositional studies on various planetary bodies as asteroid Ceres and Vesta, and also lunar surface study. And we are planning to extend similar studies on Mars and Venus. And also the research group is working on developing algorithm for hyperspectral data processing and instrumentations of like imaging and point source spectrometer in visible and near infrared wavelength. So, and today, Dr. Guneshwar Thangjam will be presenting his talk on the terrestrial planet Mercury, Venus, and Mars. And all your questions will be taken at the end of the presentation from chat. So, without further ado, let us welcome Dr. Guneshwar Thangjam for giving his presentation. Thank you.
Thank you, Nivedita, for the very nice introduction, and thanks to Dr. Pravin and the organizer of this START program for inviting me and giving such an opportunity to talk about the very important aspects of this planetary science. And I will share whatever I know about these planetary science aspects. So, as the topic suggests, terrestrial planets, Mercury, Venus, and Mars. So it covers a very huge area, and it would be actually unfair to cover in this very short time. With an objective of, let's say, to give an overview and then discuss among you about the science and technology concerns related to these terrestrial planets, and also with the motivation to encourage the younger generation, I actually prepared these slides. So the talk is actually more or less divided into, let's say, 3 parts. So the first part, I would focus on defining terrestrial planets, what, why, how, and then the second, that would be in terms of the importance or let's say the applications, and then the implications in the overall solar system, and then talking about the surface, interior, their atmosphere, and then plasma environment and so on, and then the aspects related to life elsewhere, or let's say the astrobiology. Yeah. So, and then also a little bit on technology, and then the summary and the discussion points as a takeaway message for these 3 planets in the context of, let's say, overall planetary and space science. So, yeah, now let's see what are actually these terrestrial planets. Here is actually the architecture of the so-called solar system, and in this axis, what we see is the distance in astronomical unit, and the box here, this outlines the location of the so-called the terrestrial planets, or if we extend this almost this up to asteroid belt, then what we call them is inner solar system, and while the outer ones we generally call the outer solar system, and they extend this Kuiper belt and then the Oort clouds in a far distance. So coming to this box, and then if we look, these are in a scale. And here I'm just listing down the 4 terrestrial planets. So here Earth is included because, as we know, Earth is the very, very unique terrestrial planet, and it is the home to us. And it is so unique that the science and technology is actually looking for, let's say, Earth-like planets, and why it is so unique. And for example, there is also now a science idea going on that are we alone in this universe, and where do we come from? So yeah, so in that respect, here Earth is used as a reference, and we can see the scale. And when we say terrestrial planets, so what does it mean? So terrestrial planets or telluric, these are simply, let's say, Earth-like planets with an origin from the Latin word. And when we say terrestrial, so it primarily means the planets that are primarily composed of silicate, or let's say rocks, and has a metal composition. So metal means in the form of the metallic core. And here is a very nice example, just taking Earth and Earth as a reference. So as we know that these 2 parts, this is what we call metallic core, inner core and outer core, and then mantle, and then the crust, and then what we see in the green and blue, this represents the atmosphere. But yeah, this separation into, let's say, the rocky or silicate part, and then the metallic, this is essentially the constituents or the characteristic being a terrestrial planet. Now, when we say these are terrestrial planets, so what does that mean further, or why we should care about these terrestrial planets? So terrestrial planets play a very important role. Well, as I told, Earth itself is one of the terrestrial planets. But today's talk, I'm mainly focusing on this Mercury, Venus, and Mars. So I'm starting with these numbers, and these numbers, as we know, this is the astronomical unit, and 1 astronomical unit, approximately 150 million kilometer. So what these numbers mean, and if we understand these numbers in terms of their physics and chemistry and geology, then we will be able to recognize their importance. So, for example, here I'm listing down some of the basic physical parameters: 440 Kelvin in temperature, and then 737 Kelvin, 288 Kelvin, 208 Kelvin. So these are actually the average surface temperatures, and it doesn't represent the extreme temperatures, means when it is cold and when it is actually during the sunlit. And then this density. So 5.4 gram per centimeter cube, for example, is quite similar to 5.5 gram per centimeter cube. And these bulk density tells a lot in terms of the physical and chemical property and geology. And this number is also good enough to tell what kind of geologic activity or physical and chemical activity might have underwent. And here, the 4th point, I just listed some of the unique features: 85% core of this very small planet Mercury, and the 93 bar, that is, if we compare to Earth, 93 times, and this is very significant. And these numbers, if we look in detail, or if we analyze, then it will tell why it is really important. So for example, with the astronomical unit distance, right, there is a pattern, there is a trend of this temperature. But here, what I have circled, this is a kind of anomaly, and this is also something interesting we will see. And this is very simple. This is because of the very thick atmosphere. And the next point, if we look, the size, this is for Mercury is almost, let's say, 1/3, right? And then, but if we compare the let's say the bulk density, then it's quite similar, 5.4 and 5.5. And this is also something really interesting. And then the difference in the pressure bar. So yeah, so these are the points that why we are actually studying the terrestrial planets. And I think I have almost explained these points. And science and technology driven, this is a kind of curiosity. And then also depending on what kind of technology is available and what kind of science we want to do. So now let's say how these terrestrial planets are actually studied. So basically, we know the telescopes, and from a very rich history using, let's say, ground-based telescopes or very simple telescopes in the very early times. But nowadays, they're very sophisticated and very powerful ground-based telescopes, as well as space-based telescopes, and then the remote sensing concepts like orbiter or flyby. And then in the next level, it comes with the in situ exploration using a rover or similar kind of Prof vehicles, and then there's rover, lander, and then the copter. So these are the aspects how this kind of studies are carried out. And then this is also another aspect of study using samples, meteorites, or the analog materials in the lab. But for these three bodies, Mars has a meteorite analog and lots of, let's say, terrestrial analogs. So that kind of study is possible. But Venus, no non-meteorite is available. And Mercury, I think probably very rarely there are some meteorites that are expected to be originated from Mercury. Now let's come to the second part of this lecture. So the second part is what we see on the surface, and then what kind of, let's say, morphology, what kind of material do we see, and then what we infer from them in terms of the physical and the chemical activities that might have been active or still active, and so on. So this is for Mercury, and then this is for Mars, and this is for Venus. And what we can see here is if we start with Mercury, then we do see lots of impact features on the surface, and it is actually very dominant. While we do see some features that looks like cross-cutting, cutting across the impact features or basins, and these are actually large in dimension, and these are kind of what we call tectonic features. And this is also another example. While this yellow boundary, it encircles a volcanic area. And then if we look on Mars, this is what we know, this Olympus Mons, and then this is how the surface looks like, taken from this Curiosity rover. And then this is Venus, one of the highest mountain. Actually, I forgot the name. And then this is, this image is actually from radar observation. That's why we don't see the clear picture of the surface. While these image, this one is actually from this Venera 13, and as we know, there were many probes of Venera, and by that time, multiple measurements were done, and then this is actually how the surface looks like. So by looking these kind of features, what we actually conclude, or what do we observe, Then what we see, impact cratering, very common. Volcanism, resurfacing, that's also common, either in the recent past or in its geological history. And then tectonics. So, and then having said that, the formation conditions quite diverse, and there are many gap areas where we don't know. So these are some of the unique, let's say, observations. For example, evidence for water ice deposits in polar regions, because Mercury is extremely hot, and in that kind of hostile environment, surviving water ice in these polar regions, that's really surprising. And unusual environments means the very extreme environments and the interaction with such a hostile solar environment. And then here, unique geology. So Mars, there are ample of evidences that there were activity of this water, glacier, wind activity, and some of these there are suspects that some of these activities are still active. For example, there are sand dunes and so on. Those are observed or captured by many rovers. And then there's evidence for global ocean. And then when we come to Venus, then the magmatism, or let's say volcanism, is one of the very unique features. And approximately, if I remember correctly, around 300 million years ago. So it was actually resurfaced globally, and the surface features we are seeing is approximately dates back to let's say around 300 to 500 million years, and that is something really unique. And then the tectonic features, so not like tectonic plates on Earth, but it has a own tectonic kind of activity. I think it's called blob tectonics. And then either the geological activity are still active or not. And these kind of references are learned or observed from the surface observations. Now, if we look some of the other details, for example, in these terrestrial planets, the phenomena of changes or variations or seasonal and as well as climate, and this is quite evident. So here these are some of the plot, or let's say observations using Hubble Space Telescope, and what we can see is the polar ice cap, and you can see from October 1996 to January 1997 and then March 1997 how the spatial distribution of the glaciers or the polar caps actually changed. And then this is also one of the very recent literature that brings out the importance of the geological activity involving with water and what we called sedimentation and that process. So in this case, what we see is the valley network, and then the river delta, and then a very close-up boundary between river and lake, and then one aeolian dune feature. So this is just an example, but there are ample evidence of the existence of this kind of wet environment. Now, when we come to the surface, then the surface is itself a prop to the interior to understand the subsurface and the interior structure and the composition. So in that regard, how it corresponds. So this is a very nice publication, a comparative study of these terrestrial planets. And what we see here is just how the morphology looks like on the surface on a global scale. And if we have a comparative study, for example, this is for Mercury, and what we see in color, these are the volcanic units. That is with strong evidence. And then these blue ones, these are extensional structure, means tectonic activities, and then the volcanic, and then the possible volcanic units, and so on. So this is for Mercury. And then if we look to the Mars, then what we see is the larger ones and the smaller ones, and then so many tectonic features, the blue lines and so on. And if we look to the Earth and Venus, then it is really something extreme. So for example, in case of Earth, as we know that volcanic units is quite dominant, and then we have plate tectonics. That's why this kind of tectonics has divergent plate, convergent plate, hotspot, and then there's rip zone and so on. So so Earth's really, that's why it's really unique. So if we look to Venus, then what we see is that the impact craters, which are actually dominant or presently or commonly present in the rest of of many of these planetary bodies, is not the case. And this is telling that this is something really different how it works. So whatever this the black dots, these are actually the volcano, or let's say the volcanic features, and then the colored ones is volcanic units. So we see that it's full of this kind of structures, and then there are some extensional structure system. As I mentioned, Venus has its own tectonic process, so-called blob tectonics, and these tells that not just the surface features or process, but also something very important to the interior. And when we talk about the interior process, then it's really good to understand how the volcanism or the magmatic process went out, and then how long it was active and so on. So in that case, this is a very nice comparative plot, including Moon, Mercury, Mars, Venus, and Earth. And here I have just included the surface morphology, or let's say those plots, how it looks like. And if we see, for example, Mars around 1.5 up to 1.5, the major volcanism was actually there, and then intermittent volcanism continued. And then, it came out in 2020, and there are some new results. For example, Moon, here it listed 2.5, but now it's gone to 1.5, or possibly up to, let's say, 1 micron, 1 billion years from the recent sample return mission by China. And so the knowledge is updating from time to time, and that's how the science and technology progresses. Now, when we come to this interior, then we see what is actually the understanding so far for the interior. So yeah, this is also from 2019, and some of the updates are there. Some of the updates I will cover, but I have chosen this one because it's a nice comparative study, including not just the interior structure or the interior geology, but the interior physics and chemistry, or let's say the overall science aspects. So if we let's say Mercury, for example, or Mars, or Earth and Venus, then here we do see what fraction of the core, and then the mantle, and then the transition zone, and then the upper mantle is there, and then the crust and so on. And this small one, this is the asteroid Vesta, and this is really small, just 250, around 250 kilometer in radius, but it is also considered as a kind of small terrestrial planet because it does exist as a kind of metallic core, and then the silicate mantle and the crust. Yeah, okay, now coming to this plot, this tells something very important in terms of their chemistry and, or let's say the thermodynamic property. So here we do see core fraction, and the y-axis is the iron oxide, and then this iron oxide, this is incorporated into the silicate minerals or the silicate rocks, and then so there is a correlation of the metallic iron or the iron that has gone to the iron alloy in the core, and we can see this plot: Mercury, Venus, Mars, and then the Vesta, and then the Earth is also given as an example. So in planetary science, understanding or probing the interior is actually very challenging, and most of the studies or references are taken from the surface studies or remote sensing studies, but there are some very nice geophysical kind of studies, and Apollo, for example, is a very nice evidence or the science. So now, before coming to some of the internal aspects, I'm just trying to cover these terrestrial planets, the importance in terms of the astrobiology. When we say astrobiology, it is something related to the life, origin of life, origin of life building complex organic molecules, and also water. So, as we know, nowadays there is a concern and the need for searching life in outside the solar system, so-called exoplanetary science, exobiology, and searching even on Earth, searching life in very extreme environments. So in that aspect, the terrestrial planets also serve this purpose. And so, for example, I'm just giving two examples here. So these phosphine on Venus, it was claimed a discovery using these two telescopes, and these data are at 267 gigahertz. And what they claim is that when this frame velocity at zero shows this diff, or let's say this feature, what they claim is that it is because of this phosphine pH3, and that this phosphine is of biotic origin, and it means that the life is thriving somewhere on Venus. But there were subsequent research works, and for example, two of these references I mentioned, and then they look the data, the ALMA data, and then this JCMT data, and then what they found is that it is within the error bars, or it is uncertain, and that's why this finding is under, let's say, question, under question. And this is an example about finding of complex organics on Mars. Mars had been remain a history of finding organics because water was there, and then the scientific community is very hopeful looking into this aspect. And this particular work by, again, Brott et al. 2018, they found the complex organic molecules, and then accordingly they actually try to model and then find out the methane budget, and this is showing a kind of a seasonal variability, and either this variability is biogenic or something related to geological activity is uncertain. So the future works are also going to work to concentrate on finding the complex organic molecules, and then to look from a laboratory, and then simulation studies whether is there any particular molecule or compound that is specifically assigned or attribute to the biotic origin. So, yeah, given the complex, let's say, physical and chemical and the geological conditions, Venus and Mars in this among the terrestrial planets remain a very potential target for, let's say, the astrobiology or exobiology kind of studies. Now coming to the technology, so this one is included because I'm not from the technology background, but when we do science, or when we want to do science, it is not possible without the technology. And in that respect, the innovative ideas that comes out, it makes those science dreams possible. And that's why the technology is really, really very important. And I'm just showing an example. This is Indian Space Research Organization's MOM orbiter. And in the background, what we see is this Mars, Mars orbiter. And then this NASA Curiosity rover, as we have seen in the earlier slides as well. So many rovers were actually deployed, and then recently, a few years back, China also deployed one rover on Mars, and India is also planning to deploy a rover, if I understand correctly. So Mars is in a sense very heavily explored and in very detail. And these two figures, it shows something really, something very innovative ideas. And this is actually from this NASA's Perseverance lander. And then in this Perseverance, there is also the facility to sample and then to analyze on board and so on. So these figure shows the animation, how the sample drilling is done, and then and you can imagine that very sophisticated, or let's say detailed analysis. For example, gas chromatography or mass spectrometry, these kind of studies that would even tell the isotope studies, isotope information, and so on can be brought out. Having said that, these kind of experiments are also not new, but these mission has incorporated even powerful analytic facilities, and this is something very unique for this mission, the Ingenuity helicopter, and this is a kind of concept to study the wind speed and then how the near surface pressure works and so on. And you can see this kind of this was these kind of concepts would help to mobilize and then to look into different areas and so on. And this kind of concept is, I hope, going to fly or work very in the upcoming missions. So so technology is really something very important. Now I will come to the third part, that is the recent advancement or the future scope. For example, Mercury. So here I will start with the left, the right figure, and the right figure, it's showing how hostile the environment is, because as we know that this is the closest planet, and being closest to the sun, the very energetic solar winds or the rays or the particles, these are actually in contact with with this planet, and then how such a, let's say, the magnetosphere and then the plasma environment is actually built up, and then how it works on. And it shows the prominent features and then the temperature profile and so on. Now this left figure, it tells something about this Bepi-Colombo. So the Bepi-Colombo is in route, is on the way, and I think it is arriving in 2025 next year, and it has planned to study the internal structure. Let's say whether the core has still in a liquid form, or or how it is related to its the dynamo process, or let's say the magnetic magnetic intensity, and then how the surface looks like. For example, as we know that the surface of Mercury is basaltic in general, but it has very enriched sulfur, and then this carbon, and then and as I told, a very recent study in 2022, I think, yeah, 22 or 20, I forgot. So that paper brings out that the core radius is approximately 85%, and this is something really unique, and this kind of studies are being planned. So now when we come to Mars, this InSight probe, this is something really special, because as I told, most of the studies rely on the surface or focus on the surface or near surface or their environment. But this InSight, this is just after the Apollo experiments, this is a kind of direct probe to look the interior characteristics. And this is the cartoon showing the InSight lander, and then some of the features, and then the rover. So the importance, it is showing the Mars internal structure, the best we know from the models or the observations, and then these InSight, these are some of the results. The core size, for example, 1,810 to let's say 1,800, and then this is approximately half of the Earth, and then these lighter elements, for example, oxygen, should be there in addition to iron and sulfur. And the upper mantle 700 to 800 kilometer below the surface, and then the thickened material because of the based on their observation, and the crustal region 8 to 11 kilometer. This is highly altered or fractured, and then the seismic attenuation is approximately 3 times compared to the moon, and it tells that some amounts of volatiles are expected. So yeah. This is something about the atmosphere or the exosphere and the plasma environment, and how such a environment can be used to infer many important aspects. So this figure, this shows, let's say, the electron density in the day side and the night side in this ionosphere, and then we can see the tentative layering, troposphere, mesosphere, thermosphere, and so on, and then how this electron density profile vary with the altitude, and then how the forcings are actually affecting or participating, and then how the components are actually affecting because of these processes. And this is just showing the interaction of the solar wind protons, and how the magnetic field or the magnetic tail is actually is responding. So yeah, and this is a kind of future concepts, and this Mars exploration program I just pick up because this is a very novel concept, and from NASA, and what they planned is based on 3 scientific questions or agenda: explore the potential for Martian life, and this is something we talk about, astrobiology or exobiology, and support human exploration of Mars. So after the human exploration on Moon, after this Apollo, there are no any main mission. So for Moon, it's coming with the Artemis mission, and then also with this Chinese space agency, and I think India is also planning the human human exploration on Moon. So this is something for Mars, and then the dynamic Mars in terms of the surface and subsurface or internal physics and chemistry. And then this is just a timeline. It goes up to 2040 and so on. And then we can see follow the water, for example. This is one of the well-known idea. So the idea is motivated by the fact that when water is there, it gives or paves the way for thriving the so-called life, because it will allow to synthesize those the required biomolecules and then habitability and so on. Okay, and then now I will come to Venus. So Venus, as we know, there were several missions on Venus, but in the recent past, almost abruptly, 2 missions from NASA, this Da Vinci and then the Veritas, and then one from European Space Agency, Envision, and then one from ISRO, Venus Orbiter Mission or Sukrayan, and then one probably from China, and then the Russia. These are into our information, and we can see that the importance of exploring such a planet that has been actually remain unexplored. So, well, it also doesn't mean that it was actually not explored. It was visited by many spacecrafts. It was and also very dedicated studies were also done by, for example, this Magellan mission. But because of the very thick atmosphere, probing the surface and the subsurface, that remains a very big challenge. And because of these complexities, it was remained, let's say, largely limited to the exploration. But now innovative techniques and an instrumentation ideas are coming out in order to probe the surface and then the atmosphere, its plasma environment and so on. And this is really something very extraordinary. And this figure, I have chosen this, it actually brings out the ideas of, let's say, the mantle convection, and then the process related to the surface, and then how the surface is actually interacting with the atmosphere, and then how it actually evolve with the space environment. And then we can see that in terms of the geological process or the physical process, how the lead accretion, and then in the recent time, how the activity are actually could be linked. And this is a very, I would say, recent results from this Bepi Colombo, the mission to Mercury. So it had a flyby to Venus, and that they took some of the observations on Venus en route. And then what they have done is that with these wavelengths, the brightness temperatures are actually observed, and then this brightness is compared with the recent find recent observations, and then it shows the temperature profile with this altitude and so on. So it is up to starting at around 55 because the lower atmosphere is really obstructed or limited to look into detail. So now I'm coming to my summary slide or final slide, and this is just bringing out what kind of science and technology questions could be there, and how a person like me or you can actually contribute. So when we want to contribute in terms of science and technology, we should have a very straight understanding, very motivated mindset, what I'm going to do. And it means I should understand and digest the problem. What kind of scientific problems are there? What kind of technology problems are there? And what my community is doing in terms of, let's say, the science and technology exploration. And that's why I took the global context. So if we look here, this table, it is from the European Space Agency, their Cosmic Vision 2015 to 25. So these Cosmic Vision, and it lays out 4 important science questions. What are the conditions for planet formation and the emergence of life? How does the solar system work? What are the fundamental physical laws of the universe? How did the universe originate, and what is it made of? So it is not just the terrestrial planets, but as I told, planetary and space science in general. Okay, and this is something also interesting from United States National Research Council, or their document, so-called Decadal Survey. And you can see visions and voyages for planetary science in the decade 2013 to 2022. So there is also another recent Decadal Survey from 2033 to 2023 to I think 2033. The broad science directions are more or less similar. Here I have taken these 3 because it looks something very correlated with the terrestrial planet. And you can see understand the origin and diversity of terrestrial planets, because terrestrial planets are something that really important and easily accessible, and we can do lots of, let's say, experiments, and then we can understand our closest neighbors. And then the second one, understand how the evolution of terrestrial planets enables and limits the origin and evolution of life, something from the terrestrial planets, starting with the terrestrial planets, and understand the process that control climate on Earth-like planets. And then this is from Astronomical Survey Society of India, the Vision Document 2023, and then it also lays out the 3 aspects: comparative planetary science or comparative planetology, where we compare different planets, including the outer planets as well, but planets or targets that are comparable, and then near planetary environments understanding, and then small bodies including near Earth asteroids. So keeping in mind the vision documents from NASA, from United States, from European Space Agency, and also from Astronomical Society of India, I just summarize just 2 points, and these 2 points is that I'm bringing now terrestrial planets as a topic, because I have to conclude it with the terrestrial planets. And in these terrestrial planets, these are key to understand many open questions, understanding studying the formation and evolution of our solar system and the planetary systems. And when we say planetary systems and this kind of studies, it encompasses surface, subsurface, atmosphere, exosphere, their atmosphere or plasma environment, and how the sun and the planet interaction is also happening. So it has lots of, let's say, applications, and then lots of open questions. And then second, as I told, technology. So it should be, the science should be innovative, something that would be justifiable, and in terms of technology, in order to achieve that kind of science. And that has yet to be conceptualized, and the many missions are coming. So with this, I conclude the session, this talk, my slides, and these are from different sources. And what I have shared is just a kind of a drop of water on the sea, and any suggestions, comments, and corrections are welcome. And yeah, looking forward to the discussion.
Thank you, sir, for this great talk. We can take, I think, 1 or 2 questions as for the time limit. And if you can write down on your chat the questions, we can take it from here. Are there any questions? Okay, we are getting few. So one of the question that has been asked by Dharani S is, sir, why the planets Mercury, Venus, Earth, and Mars doesn't have ring system or asteroid belt?
Okay. Yeah. So the inner planets, for example, they don't have these ring systems because their gravitational pull is, I think, not that sufficient to hold those kind of materials, I would say. And the asteroid belt, so for example, this asteroid belt is in between Mars and Jupiter, and then KBO is also another small body belt. So that is given, their gravitational pull, I think. So, I am actually not, from this, let's say, planetary mechanics kind of field, but I think it's something related to their gravitational pull.
One last question. So why Earth and Mars have almost the similar temperature as by Panchal Kumar?
So Earth and Mars. So, Earth and Mars, the temperature is actually not that, let's say, similar. And here it is 288 Kelvin and 208. And as I told, Mars doesn't have a kind of atmosphere like Earth does. So the temperature on Mars would be very extreme. And so this is just representing the average surface temperature. So they are actually not, similar.
Okay. Maybe one last question can be, one more question can be taken. Like Pedada Siddhi has asked if ISRO is planning to send any rover and a lander over Mars, and what will be the time delay for transmission reception, and also will India bring back the samples in the same mission without any fail?
Okay. I think there is a concept or kind of discussion going on, and the rover and the lander, I think, is being planned or might be planned in this second Mars orbiter mission. And regarding the timeline, I actually don't have that much information, but maybe if it comes out, then maybe by 2030 or in that time frame. But the sample return, I don't know. Because bringing samples is something another level of technology. And in planetary exploration, it is a kind of learning curve. We start with remote sensing observations, and then when we are able to understand in close details, in fine details, then we plan the next level of exploration, including rover, lander, and then when that kind of technology and science is able to execute, then the third level, or let's say the next level of exploration, that is bringing the samples back. And then we can say after that level, then maybe the human missions. So yeah, so following that kind of let's say principle, I think maybe it's good, or maybe the plan is for with the rover and the lander.
Thank you, sir, for answering all the questions and for this great presentation. And I hope that our young scholars have been inspired by this and will pursue a great career in planetary science. Thank you. And have a
Thank you. Thank you. Thank you.
Thank you, Professor Guneshwar Thangjam, for an informative as well as an inspiring talk. And also my thanks to Ms. Nivedita for well moderating the session. Thank you, both of you. So all the participants, we will be meeting tomorrow at 3:30. So we will meet again tomorrow. Thank you all.
Okay. Thank you. Bye.